In this video, we're going to introduce a nice structure that is available in this set of Pythagorean triples. Before we do that, we're going to kind of slightly transform this equation, which uses the fact that each of the term in this polynomial in three variables is all the same degree. Degree is always 2. This property is called homogeneous, so this entire thing can be called equation derived from homogeneous polynomial. Each term is degree 2. Then you can do the following. If z is non-zero, you can divide both sides by z squared. You can put it underneath the square part. Down there is a z. There, the squared y divided by z squared equals 1. So we can turn these integer solutions, the triples of integers, into a pair of rational numbers with the same denominators. So this means uncircle as follows. For example, having these 3, 4, 5 Pythagorean triple, it means you can put it in a unit circle like this, where the x-coordinate is at 3 and y-coordinate is 4, and this is an equation of radius 5. So it's 5 squared here. This process, it seems like we're looking at a circle of radius 5, and see if you look at it here, it's a circle of radius 1. So if you go through the process, we're looking at all different sorts of Pythagorean triples, maybe primitive ones. Then if you divide everything by the right-hand side, then we're entering the same size of the circle, namely the unit circle. So this one divided by 5 will explain what is happening to that. So we're actually shrinking all those Pythagorean triple with a different radius, possibly in bigger, necessarily it's getting bigger and bigger, all shrunk down to unit circle. So for example like that, suppose you shrunk it down so that the radius is 1 and the coordinate here is now 3 over 5 and 4 over 5. If you have 5, 12, 13 triple, Pythagorean triple, by dividing everything by 13, you're going to enter a coordinate like 5 divided by 13, 12 divided by 13. But they'll all appear in this unit circle, right? So all the Pythagorean triples can shrunk down to this unit circle. So you will find all the Pythagorean triple in here as rational solutions. So here's a summary. So we were looking at originally this Pythagorean triple, the typical, maybe the first example of non-trivial example of Diophantine equations. Then we turned that into a rational solution of this unit circle. And it was possible because of the property of this Pythagorean theorem, the equation being homogeneous polynomial. And I was saying the main point of this video is about this introducing the structure of the solutions. And it's done by entering the higher number structure number system than integer or rational numbers, which is namely rational numbers, which is denoted by Q, together with the imaginary number in the complex number system, Qi. So these are all numbers that consist of this shape, A, B, I, where A and B are coming from rational numbers. And although it looks like this, and it adds all the reciprocals of this number written back into that form, so it becomes a field. All the non-zero number, as identified as a complex number, has its multiplicative inverse back in this shape, which is done by multiplying complex conjugate to the denominator if you have the denominator of that shape. So that as we enter this number system, it reveals a nice structure into the to the solutions of these rational solutions of this equation. So it's done like this by entering the factorization. X plus squared, x squared plus y squared is, if you factor it using this plus, turn into negative, and negative shoved inside x squared, and you can easily verify this is same as x plus yi times x minus yi. and this one is a set equal to 1. And from this equation, we're going to pull out exactly the same shape, real part plus another real part times I, imaginary part, and exactly the same component with opposite sign and keeping right hand side equals 1, doing the slightly different order of operation. So watch this, what happens. If you raise both sides to any nth power, let's do that for second power first. So if I raise everything to the second power, you have second power here, x minus yi, you have second power here, right hand side still remains 1. So if you raise the third power, fourth power, right hand side is going to be 1. And what happened, the magic that happened, is that you don't multiply this one first. We're going to do this second power business first, and then we're going to look at this two component and realize that they have exact symmetric shape. So if you multiply this to itself, being careful with that, whenever you have I squared, that it becomes a -1. That's the property of a imaginary number. What happens if you square that? This is the result. So here it is. If you, after you square this one, if you collect the part that does not have I in it, so that's this part, that's definitely a rational number. Everything that has I in it is collected like this. If you do the same thing, only difference is that exactly the same component except the sign in here. So it's like this, exactly the same part. So you have to notice that what happened, and you will see that if something magic happens here. The secret behind this magic is that after you raise this the second power, or if you believe after this simple example, after the third power, fourth power, whatever, you might believe that they always have the same shape all the time. So namely, this real part in the first factor and this real part in the first factor is exactly the same, and this imaginary part component has exactly the same magnitude and opposite sign. So that allows us to rewrite this one exactly into square plus square again, and keeping the right hand side 1. So you can look at this as if the whole thing in here is a plus b, and this is exactly a, and this whole thing is b up here. This is a minus b. So you know a plus b times a minus b is a squared minus b squared. So you have this squared, x squared minus y squared, whole thing squared, plus this thing. Turns out it's negative, it's supposed to be negative squared, but this I squared and I squared together becomes -1. So negative b squared becomes positive square of this 2xy part. So you have 2xy squared equals 1. So what just happened is that after you factor it and raising to a higher power, magically kept exactly the same symmetric shape, and therefore as you multiply back to different order, square first and multiply out, not multiplying out in a square, then you'll be able to see that result has this nice shape. But just for fun, and you will see, so the summary is that out of x squared plus y squared equals 1, if you have a one solution, just like 3, 5, 4, 5 that we had before, then you can create the new solutions. And you will see that after you plug in this number in here, this is really different solutions. So numerator and denominator does not have any common factor, so it's really different rational numbers. But let me go ahead and try different thing. I'm going to multiply this one out first and then square it later. There will be different order of operation, and compare it with this one in here. So all that I did over here is really calculating this. This together is still x squared plus y squared squared, but we multiply this one out first and then square it, and it's easy that it's x to the fourth plus y to the fourth plus 2 x squared y squared equals 1, and that's what that is. So if you compare this left hand side together, and you might recognize, oh, that's really the same. It's easy to see that if you just expand this one, you get back to here. You pick up negative 2x squared plus times y squared. Here's a positive 4x squared y squared. That'll give you a total of 2x squared plus y squared. So you can easily verify that without entering any of this complex number, this this thing is still true. So for example, I ran this computation a couple of times. I started with this first solution, 3, 5, and 4, 5 into a unit circle, and then I ran through, calculated the difference of the squares of these two things, and 2 times the product. That gives you this first solution. So I started from this again, and I repeat this algorithm. Look that let x be this negative. You can take that a positive, it doesn't matter, and y to be this number, and go through this computation again to generate another solution, and so on. So that gives you another nice way to generate more and more Pythagorean triples, namely these are 3 2 sides, and that's going to be the hypotenuse. In the early examples, we saw that, and by asking natural questions on how can we keep this one a part 1 and a part 1, and here can we keep generating that kind of thing, and then we're successful in that. And here's different type of a fast way of generating Pythagorean triple based on this higher number system and the algebra, and in this higher number system that's really happened. So I'd like to call this method in here more algebraic approach. It's algebra of higher number system. I'm going to continue with this algebraic method and show you that if you happen to have 2 solutions, x and y, x and y, and z and w, if you go back, I don't know if you can see this or not, but if you look at this formulas, this up there, and all that it's doing is an adding and subtracting, and in that process of arithmetic, you always have the 5 in the denominator. So these are all powers of 5. So this 25, if you square it, I'm sure it gets there. If you square it again, it becomes this number, and so on. But if you happen to have totally different solution, for example, one comes from, let's say, looking at this 3, 4, 5, and also we have this 12, 13, and 5, 13, right? So if you have these 2 solutions, and we'll see you can actually use the same method so that we can combine these 2 solutions to come up with a new solution. So idea is that you go through the factorization again, x plus iy and x minus iy equals 1. You write down the same thing in here, like that. Then rather than multiplying, so again, to keep the right hand side 1, one thing we can do is multiplying these two each other. Then you can see the right hand side is still 1. When you multiply this one, maybe we can multiply this shape and that shape, and in that case we happen to keep this symmetric shape. And after we multiply these 2 factors with a positive I, and the negative I is supposed to be here, then it turns out the result of the product of these 2, product of that 2, happen to have a symmetric shape. So if you multiply these 2, and you get this one xz, that's the rational part. As you multiply these 2, I squared becomes negative, and those part that have I in it is cross multiplication, and you get in here. And you continue with this one, and you get exactly the same thing except the sign in the middle there. So we have this solution. So you can see this is a real part of this imaginary number, and this is the imaginary part. They have the other factor that has exactly the same component except the sign. So these are complex conjugate to each other. So if you multiply this one out, we have the same phenomenon. You have xz minus yw squared plus this 2 becomes a positive because of I squared, and you have xw plus yz, all things squared, equals 1. So if you have 2 solutions, rational solutions, and here it tells you how to combine this through the simple algebra field operation, namely addition, subtraction, multiplication, division, you can arrive in a new solutions. So I'm going to use these 2 to generate a bunch of other solutions in here. So when I went through this way of generating a new function with these 2 points, so x being 3, 5 and y being 4, 5, z being this number and w being that number, when you went through this law, this xz minus yw is this number, and xw plus yz gives you this number. And if you think about what happened to the denominator, you can easily see that must be the product of 5 and 13, which is what you see down there. So we have this new solution, Pythagorean triple. So I went ahead and played one more combination. So I play with it again with the 3, 5 and 4, 5 in here. So I looked at these 2 points. So I let this one as xy, that one in the zw. When I play with these 2, I got this point right here. That is negative 204 divided by 325, and 253 in the numerator and 325 in the denominator. So from there you can keep generating and different type of shape where the denominators are the powers of 5 and 13. So what we really have accomplished here is a rational solution. So let me call that the z, the rational solutions, x comma y, and it satisfies. This is coming from all rational numbers. So I'm going to write as a Cartesian product of 2 rational numbers, set of rational numbers that satisfy this unit circle equation. Then whenever you have 2 points p and q that is inside the z, not that integer z, just the set z, 0 set, that's usually what they say, and we introduce this law of kind of combining these 2 coordinates of these 2 solutions to get a new solution that is sitting inside that z. And we will use this addition notation to denote the process. If you have x and y coordinate there, if you have x and y coordinate there, and this is going to be a way to generate a new solutions. Namely like that, if p has x and y coordinate like this, and q has zw coordinates. So if you have 2 points, you go through this law and make this x coordinate and make that y coordinate, and that's going to be still in this unit circle. So this is like an operation. So definitely if you have 2 things, we can generate another solution. So we have actually defined a binary operation on this set of unit circle. So before it was just a pure set collection of positions in xy plane with the rational coordinates. Now we introduce this structure, which is the term that I used before, but the better term is really this binary operation is defined. It's not really hard to show that this binary operation has a really nice property. For example, if you have usually the operation, we expect this something called associativity law holds. So if you do PQ first and then do R later, which is what we did earlier, if I go back a little bit, I have these 2 points done and then do the third operation. This is exactly represented by these 3 points in here. But you can do exactly the same thing, get exactly the same result by doing the slightly different order of operation. You first do this QR first and add to P later. The addition here is this complicated way of generating the position, not that the vector addition that you usually learn in calculus. That's the difference. So this binary operation holds, and this associativity. Also, we have this interesting point E, that's 1 comma 0. That is definitely a point on this unit circle. Then we have this property that if you combine it with any point, you don't get anything new, but you go back to itself. If we interpret this as a kind of additive operator, then it serves as an identity or 0 element. You add 0 to something and you get this one back. And third property I'd like to introduce it here is that it doesn't matter if you do P and Q in this order. If you swap this order like this, a role of x and y and zw, and if you go through, they're exactly the same. So we have this type of property. So I went through this nice structure because this type of structure is still available when we enter higher degree polynomial equation into variable and when we look at the rational solutions. So this is a really good prelude to the more complicated structure, but we pull out exactly this type of property in a higher degree.